Okay friends, so now in this video I will demonstrate how we can do electronic density of states calculation by using ELK code. Well, for that I'll be going to this work directory folder. Usually I work in a folder namely work directory. So here we have opted for aluminum as an example for doing electronic density of states calculation. I think earlier videos I was running things in examples folder of ELK. So now I have shifted to a general case if you have to work in any directory and then how you can do the calculations. So here what we need is we need to make a directory in which we want to work. So in our case we have made it by the name aluminium AL, or you can name it like anything. Now you have to have elk.in as usual for doing the calculations, and I have already explained this file to you, so won't be talking much about it. Task, for getting electronic density of states, you have to do first the ground state. You have to obtain the ground state charge density within density functional theory. So well, task 0 is there, and this n grid k is something which is important parameter. You cannot ignore this. So by default it used to be, I think, 444. I hope you remember that. So let us go with this, and then I will show what is the importance of this thing, and also pay attention to, okay, that I will highlight later on. Just hold on. Let us first obtain the ground state. So we just need to run the ELK code. Yeah, we are done with the ground state. So fast it is, right? Yeah, so total energy is there. I hope you remember this. Now what we need is we need to go to elk.in, and then I hope they have mentioned even in the example itself, task 10 is for ground state electronic density of states. So here it is. We are done with this. Now you have to run ELK code with task 10. So yeah, we are done with the ground state density also. It's very fast for simple cases at least. So you will be getting some files, namely latest files are like, let me show it for you. ls-lrt is the command which actually tells you the files in the order of time when they were written. So the last file which was written is tdos. Then after that the code have written pdos, idos, and elm rep. So we will be mainly focusing on practical things as of now, not too much into the theoretical details. So the practical file which is of interest is tdos, which refers for total density of state. Okay, I had made a small demonstration for you to actually show what is this electronic density of states. Let me check if I have that folder in my, yeah, I think it was here. It was a small PowerPoint presentation just for demonstrating quick physics of what is electronic density of states for those who are not familiar with this. If you already are familiar with this, you can skip this portion of the video. Let me quickly just show that. So what is electronic density of states? This is the important question which as a students or as a beginner you may have. So when you talk of atoms, in atoms you have electronic energy states which are discretized, and discretization is very fundamental characteristic of the quantized systems. So atom is one such system. So you have energy states at a particular you have the states at particular energy value. For example, for hydrogen atom you have energies being given by minus 13.6 over n square, means the energy is a function of n, the principal quantum number. Then as you head on to the more and more complicated atoms, there you may find out that energy is not just the function of n, the principal quantum number, but it may also vary with L and M and S. For magnetic atoms you may have spin dependence as well. So main message here is that the energy states are discrete, and you would find out huge gaps between the energy states for an atom. So what happens is, now here we are talking of solids, and specifically the periodic solids. So in periodic solids, means the crystals, when the atoms come together to form solids or to form the crystals, what happens is that the deeply lying energy states, or what we call the core states, they remains almost as discretized as they are in the atoms. But the valence electronic states splits into closely spaced energy bands, and that's what we call the bands which are formed in crystals. So these bands are important, and we need to actually know how the electronic energy states are distributed as a function of energy in these bands, and that is what we are trying to calculate. Means that is called the density of states, means how many energy states are in a particular energy range. So that is how this is just a schematic representation of density of states. These bands now are represented in the way we represent these in with the help of electronic density of state. So this is how they looks like. Means if you try to see the core states, so in density of state graph, this y-axis is density of state. These core states looks like sharp delta peaks. Now depending upon which particular states are they, the peak height is there. So means height of this peak is actually telling you how many states are lying in a particular energy value, dn, number of states in particular energy range. So for core states, they are very, you can say, localized, like Dirac delta functions. And for valence, or the bands where the band formation is happens, where the band formation happens, you may find out some continuous variation of this dn over de, or the density of states. So there may be regions where you may have a large number of states. There may be regions where you will not be having any states. Moreover, when there is no states here, so you would find out that density of state is 0 there. So similarly, the density of states between any two bands is also practically 0. And that is how, this is just a arbitrary schematic representation of what kind of graphs we should expect for electronic density of states. Now there is something called Fermi level, means the energy level up to which the electronic energy states are completely filled. Now depending upon where the Fermi level lies, you may have the system as a metal, semiconductor, or insulator. We will be talking about that in the coming lectures, so I don't want to make these lectures too long. Small, maybe maximum 15 minutes demo to focus on a small property. That's the target as of now. So I hope this gives you a quicker overview of what we are going to look at, and what is electronic density of states. So for aluminum, with the help of ELK code, we have got a file called TDOS, which is actually telling us or showing us the electronic density of states for aluminum, and that's how the graph looks like. And with the help of ELK code, what they do is that Fermi level is set up at 0. So that's the internal structure of the code, or arrangement in the code. So they have fixed Fermi level at 0. So you can find out there are states in Fermi level. At Fermi level means this is metal, and that is how the electronic density of state for aluminum looks like. But here comes something important, and important thing is that how many K points we had used for calculating electronic density of states? Only 10 K points. Now is this, in last lecture I was talking about K point convergence. So first thing is, you should do K point convergence for total energy. That's one thing, and you must not miss that. But we also should see the specific properties uh, with respect to at least convergence with the convergence of a specific property which we are calculating with respect to k points. Sometimes you may find out that okay, energy is reasonably converged, but other properties, like say when we are focusing on optical properties, there we need very high or dense number of k points. So means even for electronic density of states, we will check the effect of k points, how we can see or ensure that we have taken sufficient number of k points. For that, let me do one thing, say plot this t DOS, and it is for 10 k points, or for a mesh of 4 cross 4 cross 4, and I'll keep this graph with me, and then we'll be putting other values which I am getting for higher number of k points into the same graph. So this has come for 4 cross 4 cross 4 graph, so I have marked it to avoid any confusion. So this is for 4 cross 4 cross 4. Now let me go to elk.in file, and so whenever we are increasing k points, we must do the ground state. We already have one ground state which is not very bad, which has been taken for 4 cross 4 cross 4 points. So we will take that ground state as the starting point for this set of calculation, and just increase the k points from 4 cross 4 cross 4 to, say, let me increase it in a systematic manner to 6 cross 6 cross 6. And we can integrate two tasks together in elk.in file. So here we can put 10 as well. So what the code will do, it will first do task 1, means ground state, and then that will be followed by task 10. So let us run it. So task 1 and task 10 done. Another important thing which you should notice is what is the unit of density of state. So this is mentioned here. IDOS means interstitial DOS. I'll be talking about this in the coming lectures. And you know, the units of density of state is states per Hartree per unit cell. Per unit cell means the unit cell which we have taken in the ELK code. So here we have taken primitive cell, so the density of states are for that cell. So energy is, you know, density of state is dN by dE. I hope you remember this graph, dN by dE. So electronic density of states is in say states, it's a number, how many states per unit energy means Hartree, per unit cell means the unit cell which we have used in the elk.in file. So you know, how many k points this time? It is 28. So let us plot the density of state. So what the code does is it overwrites the files. So now the tdos file is not the same as the previous one, it has been overwritten for this set of k points. So let me import that directly in XMGrace. So plot, or say data, import this file. So by default it looks for dat files. Let me go for all the files, and here we will be showing only tdos. So here is the tdos. Now can you notice there is a significant change in the electronic density of states? Let me mark it first, then I will highlight. 6 cross 6 cross 6 mesh containing 28 k points. So I'm not, you know, I'm not putting how many k points, I'm just talking of what was the mesh size. You can do it either way. So you can see, let me make it these lines a little broader to make them visible in a better fashion. So now we need to change their color. Okay, so you can see there is a change, and means the k points was the number of k points were not sufficient in this case. So what is the guarantee that 6 cross 6 cross 6 is sufficient? We can't say. We have to ensure the convergence. So for that we have to go to elk.in and try the same thing with, say, higher number of k points, like say 8 cross 8 cross 8. ELK. Now calculation are taking little longer because number of k points have increased. So now we have taken 60 k points, and you can import, and again now file has been overwritten, so I can directly call this file. So this is for 8 cross 8 cross 8. Let me also say total number of k points put here, so that we know how many k points were taken. In this case it was 28, I think 28, and in first case it was 10. So please don't misinterpret my this representation that 4 cross 4 cross 4 must be 64, right? So it's not that thing. It simply says how many k points that 4 cross 4 cross 4 mesh had taken. Okay, so now you can see there is a difference between say 28 and 60 k points, but the difference is relatively less, I believe. In this region you are finding these this green and this red curve are trying to match, but at higher points these are deviating significantly, and you have sharp peaks in red one but not in the green one. So let us go with the higher number of k points. Okay, so let us try the same thing for say 10 cross 10 cross 10. Now I will be increasing the step size so that my video completes in the planned time duration. So again, now we are doing it for 10 cross 10 cross 10, which contained how many k points? Let me show it to you. It has 110, almost double number of k points. So this is 10 cross 10 cross 10, contains 110 k points. Okay, so now this green and blue curve are showing some sort of less deviation. Let us try it once more for higher. Let me go directly now to 15 cross 15 cross 15. Okay, now you notice here the ground state calculation is now taking little more time, because now k points have been increased significantly. Earlier it used to be just press the enter and calculation is done. So that's something important. You should notice that you can't take infinitely large number of k points. You have to maintain an optimization between computational time and the accuracy which is required. So now we did it for 15 cross 15 cross 15. How many k points it were? Oh, 344, significantly large number of points. 15 cross 15 cross 15, containing how many? I think it was 344 number of k points in the Boolean zone. To show you the things in a better manner, let me increase the width of all the lines and set up the colors. I think this, okay, that is visible here. This yellow color corresponds to the highest. Now you can see this black one was way different from the this yellow one, but as we are now approaching to the higher and higher number of k points, these lines starts to converge to each other. So that's something important, and you need to ensure that by increasing number of k points further, when the change in electronic density of states is not way much, it's not very much, in that case you can say that your electronic density of state has been obtained correctly. So here it is. We are doing last set. I'm doing last set for you, then you do it as an exercise for yourself. So now it is for 20 cross 20. Now you can notice it is taking significant time for arriving at the ground state, and it is the simple system of single atom. So assume when you will be doing calculations for realistic materials which may have bigger unit cells, then that would be time consuming, of course. And that is where you need to ensure that you don't waste too much of computational time. And yeah, so now you can see that in this case, this yellow curve and the gray one which we have obtained, both are almost overlapping, I mean reasonably agreeing with each other. You can see, yes. Let me change this color. Yellow is not clearly visible, so let me change it to orange, this specific only. Now just simply see the gray one and the orange one. So the two are reasonably matching with each other almost. So we can say this 20 cross 20 cross 20, or even a mesh between 15 cross 15 cross 15 and 20 cross 20 cross 20 would be a safer one for calculating electronic density of states. So let me just, for sake of completeness, how many k points it had taken? It was 770 k points. 770 k points. Oh, sorry, k points. So that is how we can calculate electronic density of states for any material. Right now we have done it for aluminum, the metal it is. Then in coming classes, coming lectures, I will demonstrate it for semiconductors as well, and then highlight their one important limitation of density functional theory, but that will be following up in future. So to keep my video reasonably short, I am now stopping. So I hope this is clear how we can do calculation of electronic density of state for any material. So you try it for other materials as an homework. You can try it for copper, you can try it for other metals only. First focus on metals, and then just try to see that how we can check the convergence of the electronic density of state. So that's all. Thank you.